Satish sir, shall we start, sir?
Yes, ma'am. Yes, ma'am. We can start.
Okay. Okay. Happy evening to all of you. Um, on behalf of Department of Electronics Engineering, I welcome our today's speaker, Professor John Jose, Department of Computer Science Engineering, IIT Guwahati. Hearty welcome, Professor. Now I invite one of the coordinator, Dr. V. Satish Kumar, sir, to give introduction about our expert member, Dr. John Jose. Over to Satish, sir.
Thank you, ma'am. So it gives me immense pleasure in welcoming Professor John Jose, sir. Professor is from Department of Computer Science and Engineering, IIT Guwahati. So Professor has more than 20 years of experience in teaching and research-related activities. Professor has obtained his PhD from IIT Madras in the year 2014. Professor's research interest includes multi-core computer architecture, network on chip, and cache optimization in tiled chip multiprocessor, machine learning based domain specific accelerator for NOCs, non-volatile memory technology, secure system on chip design techniques, and disaggregated memory management in data center architectures. So Professor has over 60 IEEE and ACM peer-reviewed conference publications, over 25 ACM and IEEE transaction papers as well as in Springer as well as in Elsevier journal papers to his credit. So today Professor will be delivering a talk on redefining computer architecture for future AI and ML applications. Now the session is over to you, sir. Hello, sir.
Okay. Can you hear me now, Satish?
Yes, sir. Yes, sir. Yes, sir.
Okay. Thank you for the opportunity that is given to me today. It's an honor to be here as a speaker. I once again congratulate the organizing team for planning an FDP program through the ATAL scheme of AICTE. It's good to have large number of participants joining online. We would always like to come to Chennai and then take the session because Chennai is very near to my heart. I spent 5 years there in Chennai. But the scheme is online, so I would try to go with the schedule that has been given. It's good to see a lot of participants, and then I hope this is the towards the end of the workshop. It started from Monday onwards. So you might have heard about different talks that is aligned to this. So today my talk is about redefining computer architecture for AI and ML applications. So this is a very, very important and emerging area especially when you live in an era of AI. AI is in our daily life, and AI on hardware is going to be the next revolutionary one that is there. Machine learning and AI is everywhere. We know that nowadays it is making a lot of noise in every domain. People sometimes from electronics or other little far off from the core AI may feel that we are not with the wave. So this talk may be pitched up in a different way where we have to understand ultimately AI is a kind of an algorithm. It's a special class of an application where a computer program can mimic human brain. So it's just like any other program, but the impact, the way by which this effect of program is going to be phenomenal. That's why there is a noise, there is a huge wave in AI. We have to understand that once you talk about any program, be it a sorting program, a tree searching program, or a database entry program, anything, ultimately it is going to run on a computer hardware. A hardware consists of a processor plus a memory, some IO, some storage. So the question is whether our conventional hardware that we used to have will flourish in the AI wave also. Is there any difference, or do you find any limitation in our conventional von Neumann architecture consisting of processors and memory and fetching and decoding program and then doing? So we need to understand that with the kind of data intensive new generation programs, there exists a limit to which the performance of conventional programs, conventional hardware can be. So that is the reason that we are going to talk about AI in daily life and how an AI hardware can help. Probably this would have been one of the first diagram that we learn in a microprocessor or a computer organization course. Processor memory interaction. We know that there is a processor which is the heart of any computing system, the brain of any computing system. It's connected to a memory where you store your programs. And from there, you are going to fetch instruction by instruction, what is given in the left side. Then you decode the instruction, fetch the operand, then execute the corresponding operation, store the result, and then we move to the next instruction. So we have some registers, some control units which will facilitate this. Now let me talk about von Neumann bottleneck. Imagine you are talking about a very simple instruction, move R2 from location 1000. So what I wanted is the content of location 1000 need to be moved to the register R2. So it's a movement of something from memory into a register which is present inside the processor. So you can see that first you give the address will pass through the address bus. And as shown in the animation, the content of some memory location, it gets transferred to the data bus. It will reach the processor and then it has been moved into the register R2. You have a very high-speed processor and a relatively slow memory, which has been used to facilitate this operation. So what will happen if you are going to do this billions of times? There exists different speeds of CPU and then memory. So there is going to be a huge bottleneck that we experience because of the difference in speed. So we know that there exists a memory wall. That means because of the difference in speeds of a CPU and that of a memory. Fetching anything is slow, but when you do it over and again, it is going to be a nightmare. Now let me introduce to the concept of Turing tariff. The cost of performing certain operations. Imagine, let us say you have a CPU and it has an arithmetic logic unit which is capable of performing adding operations. Since it is a general purpose processor, anything that you wanted to add, first I need to bring the instruction because you can do many operations. So only if you bring the instruction and decode it, then only you will be knowing whether the instruction is an add or a subtract or a multiply, whatever the case may be. So it takes some time because you have to go to memory and fetch an instruction. We call it as high cache access. Roughly, let us say it may take 25 picojoules of energy. Then after bringing and decoding the instruction, then you come to know that, okay, how to access some contents of register. So accessing register may be another few picojoules of energy. And then you have to generate appropriate control signals. Everything put together. Ultimately, the end of all operation is appropriate control signals are ready to be triggered in the input of your adder. And then the actual adding operation is a very, very, very small operation. So out of a total 70 picojoule, if the overall power consumption or energy that is connected to a simple add operation, maybe only 1 or 2 picojoule, a very small fraction is the actual adding. The rest is the periphery operation which is required in order to facilitate this adding. This is what is known as Turing tariff. So the fetch and decode and generation of the control signals will take more energy than the actual execution. It can vary from 10x times to up to 4000x times depending on certain class of instruction. So what do you mean by this? Since we have a processor which is capable of performing multiple operations, you have to represent your instructions using some bit patterns. Only upon decoding, you know this bit pattern, then you tell your ALU, okay, this time you have to do adding, next time you have to do shifting, next time you may have to do some rotation operation. So accordingly, upon decoding, you come to know what is the effective operation to be carried out. So this is exactly what is known as Turing tariff. Now, if you go with the conventional hardware, then the problem is conventional hardware has a lot of Turing tariff when it comes to applications which have regularly repeated operations. So what we can do, we can redesign the architecture that are tailored for domain-specific application. We have certain applications like graphics application, where certain class of operations are repeated again and again and again. Similarly, neural network simulations, heat equation, genomics, weather prediction, all of these kind of applications have something in special. This application is heavily dominated by certain class of operations. Okay, so suppose if I'm telling, what do you mean by this? Especially if some of you are involved in day-to-day cooking in the kitchen. One important aspect of preparing any vegetable is you have to cut the vegetables. So cutting vegetable is an operation which is heavily there as far as any cooking of a vegetable is being involved. Okay. Similarly, when it comes to let us say cleaning or cleaning of a floor, then using a detergent and using a mop, that is something. Can someone please mute the mic? I request audience, if you are not speaking, please mute the mic. Okay, thank you. Can the organizers please do that, please? Okay. So I'll wait.
Voice is not audible, ma'am. Ma'am, SAS voice is not audible, ma'am.
Pro sir, your voice is not audible. Pro sir.
Can you hear me now?
Yes, Pro sir. Now we can able to hear you.
Okay. So I think in between somebody even muted me. So since you are not speaking, I may not be able to hear. Okay. So if you are talking about a neural network, then with this you will be in a position to know that multiple neurons are connected and they have weights. And based upon this convolution operation that you do, if the output is going to be above a threshold, we tell it's a cat. If the output is below a threshold, we tell it is not a cat. Similarly, this is a decision problem. Given an image, can you tell whether it's a cat or not? Similarly, there are many applications where given an input, you will be in a position either to classify it or you are going to separate it or not. Now, given a neural network like this, what is the equivalent representations? What is a logical block when it comes to an electronic circuitry? So the inputs can be represented as I1 and I2. That is the input values. And then you have some set of neurons. That's your next layer. Inputs are multiplied with weights. So if you look at that, I can represent the neural network with the help of a matrix operation. It's a weight matrix multiplied by the input matrix. And what you see is W11 into I1, W12 into I2, like that, you can get a set of products. It's basically a multiply and then accumulate. Matrix vector product is the operation. So what is this image? If you look at this image, If you look at this image, you are able to find out that given an image of a car, ultimately you have to tell whether this is going to be a Volvo car or not. So you can see that it also is been modeled with the help of neural network. Multiple inputs are there and the inputs are connected to the next layer with weights. I have to multiply these weights. The values are there. So how do you all do this? Because you all know that there are two phases. One is a training phase and the other one is inference phase. Training is a process by which you determine the weights and apply the corresponding bias. Whereas inference means, can you apply these weights to check whether a given value is acceptable for you or not. So now if you look at the training means, let's say an image is a cat, and then first you pass it over, and then you see whether you are getting the desired output or not. If not, you are going to redefine your weights once again. So the inputs are given and the weights are being adjusted until the output reaches the expected output. This process of redefining the weights is known as training. Once a system is trained, then given a new input value, which is called as an inference value, and then with the inference, you are supposed to pass through the neural network and then tell whether an inference is being made. So given an input, you have to tell whether it's a cat or not. It's exactly what you see. Now, what are deep neural networks? When you have lot many layers, then you call it as a deep neural network. You have an input layer, you have an output layer, and then you have one layer. It is the computation layer or the hidden layer. When you have lot many hidden layers, then we call it as a deep neural network. So it can mimic more complex operation. Given this background, let us now try to understand how are you going to do this operation on a hardware. So look at this hardware that has been given. It's a multi-core processor. Okay, where P represents processing element and R represents the routers that connect the processing elements. So we have a sequence of processing elements and we have to do such that each node given in the deep neural network, its operation. What is its operation? Input multiplied by weight. It has to be carried out in one of these P. So this task of mapping means a neuron's operation has to be done in a specific processing element. What is this operation? It's a MAC operation, multiply and accumulate operation. And now the output of that operation has to be taken. It will travel through the communication fabric that you see across various routers and it reaches the next processing element and it's going to do that. This is known as a deep learning neural network and how its mapping happens. So in short, in order to perform the computation, the input value and the corresponding weight value has to move from memory. It has to reach this processing chip. It has to go to the appropriate processing element. So the input and weight value of the corresponding neuron has to reach the processing element. And after processing, the output has to travel to the next processing element, which is supposed to perform the operation of the next neuron in the network. Similarly, so this means there is a lot of data movement that is there through the underlying interconnect. So the most of the system is dedicated to storing as well as moving the data. Now, what is a deep neural network? The deep neural network consists of a lot of convolution layer and some fully connected layers at the end. Now, what is this convolution operation? The convolution operation is a multiplication of input and corresponding weight, that's sigma wi xi, plus a bias that you are going to apply. And then you have a fully connected layer. So we have an input feature map, and then we have the filters, which is known as the convolution layers, and then we have an output feature map that has been there. So in all this neural network, convolution account for more than 90% of overall computation. So it dominates runtime as well as energy consumption. So the weight has to be multiplied with the corresponding filter, and then it has to be done in order to get it. So what is convolution? Let's say you have these input values and then there is a filter. So you have to perform the corresponding multiply and accumulate operation. And then you add up, that's what your output is going to be. At the end, an activation function. So consider the case that you have 3 input vectors that is available and then you have a filter that is to be applied across all of the 3. You will get one of this value as the output. So this is the way how you get the output. Now if you slowly move the filter from left to right, then accordingly different output values have been obtained. Let us now move to the next row. So you can see that what you see on the left hand side here what you see, it's keep on moving. As and when you keep on moving, newer output values are obtained. And then I'm moving the filter to one row down, then you get this new value. And if you further move, then this is the output vector that you are going to get. So given an input, when you move the filter across, one by one, you are going to get these values, and ultimately one layer of output is obtained. Now let us see how a DNN computation happens. Can you see that we have different layers that is part of the neural network? And then these layers, how do you represent these layers? These layers are represented by input values as well as corresponding weights that is stored in your off-chip memory. That is your main memory, DRAM, we call. And now this is an accelerator circuit. Accelerator circuit are some circuit which are specifically designed, contains of multiple processing elements that is been there. So since we have multiple processing elements, these processing elements are going to perform the corresponding operation. What is the operation? It's input weight multiplied by weight. So the input has to reach from off-chip memory into this accelerator chip. The weight has to reach. So it involves a lot of data movements. So ideally, you will store in this global buffer through the interconnection. Let's say this first P will represent your neuron 1. This is neuron 2, neuron 3, neuron 4. It will perform operation and it will pass to neuron 5, 6, 7, and 8. So appropriate weight value and input value has to be there. So what are the steps involved in processing a layer I? From off-chip memory, you move the corresponding filters or weights and input feature map into the global buffer, which is inside the accelerator. Through the network on chip, its interconnection mechanism, you reach the different processing elements, and then through the NOC it will go to the global buffer back, and then it has been taken. The output feature map has been produced, what you see it as a blue color. Now let me try to introduce how convolution happens. So what you have here is on the left side is a specialized accelerator circuit, which will take care of your processing, and then you have a main memory. So you have main memory and then you have a hardware system that is available, and the main memory is already preloaded with your input feature maps and the filters that are been available. What do you need to do? You have to generate an output feature map. Let us now see what are the operations that is been involved. So the first operation is I have to bring the input feature map from the main memory into the accelerator circuit. So the accelerator circuit consists of 16 processing elements, which has been shown in small blue squares. Then you can see that it's connected to some routers. So there is an interconnection grid through which the input feature map has to travel. So first I will bring into one of the processing element, which is considered as a memory interface. Now, let us say there are 6 inputs. My first layer has 6 neurons. So in order to carry the operations of the 6 neurons, we will keep it, we will identify these 6, what has been shown in the blue color. These are the set of processing elements where the operation of the 6 neurons are scheduled to happen. We call this as mapping. So once I identify the hardware at which this convolution has to happen, then whatever is the data that has been taken from main memory, which has reached the accelerator circuit, has to reach the 6th one. So the input value and the corresponding weight value for the first neuron has to move from this MI through this and reach here. Similarly, the input value and the weight of the second one has to reach here. Input and weight has to reach here. Like that, there are a total of 6 one of them. So this is the next operation. From MI, you need to send the data. So this involves data movement. This involves application mapping. This involves neuron scheduling. So there are different steps that are, so depending on the interest of people will exploit further that. Once it has been moved, then we have to do the convolution operation. So once the filter also, similarly the filter, first you move the input, now the filter is been moved. So we have brought the filter also to MI, and filter also reaches the corresponding place. And then what you have to do? You have to perform this convolution operation. Now this convolution operation is what you have seen. Input value, which is already stored there, is multiplied with the newly arrived weight value. And the multiplied value is now stored back in the same time after the convolution. Similarly, all of them will do it parallelly, and then the result is been brought back to the memory interface. Once you get the result, then I can generate this output feature map. So in short, what you see, if you have a specialized hardware, like an accelerator, what has been shown in this picture as a 16 tile accelerator. In the 16 tiles, we, depending on, so now in this case, what we have taken is a neural network which has only 6 neurons. Since it has only 6 neurons, I'm using only the 6 blue color processing elements that has been shown. Had it been 9, then another 3 more has been chosen. So accordingly, only the inputs and the weight value has to move. So I will take a small pause here. What I wanted to convey here is any neural network application is about representing the neural network application as an input followed by weights. These inputs and weights has to be essentially stored in the main memory. And from the main memory, we have to bring them into the accelerator chip. Now your input data is there in the global chip, global buffer, and from there. So I will pause for a while. If anybody has any questions, we'll take it up the questions. I request once again people who are traveling, please mute your mic such that the others will be able to listen and then do. Any queries to anyone? Either you can raise the hand and ask query, whether you understood whatever is being conveyed till now. Is the context clear? If that is clear, I will go further, or else I will pause and then I will clarify your queries.
Good evening, sir.
Good evening.
Hello.
Yes. Yes.
So, can you show some hardware for this topic, sir? Any sample hardware? Some sample
Okay.
hardware.
Yeah. So towards the end, I'm going to show. So what you have to see is the logical diagram that you have seen. There are chips from NVIDIA. There are chips from processor manufacturing companies which work in the semiconductor field, which will generate. So these are not your conventional microprocessors. A microprocessor can do a lot of operations, adding, subtraction, square root. So these are only capable of performing multiplication and adding, because the base of a neural network is multiplication and adding. That's a convolution operation. So can I arrange a sequence of multipliers arranged, and then can I have some control circuitry which will supply these multipliers with appropriate multiplicand and the multiplier. So the name accelerator means it's a circuit, something similar to this. I will show about some sample hardware which is having that in the subsequent slides.
Okay, thank you, sir.
So I wanted you to know whether are you able to understand the flow. Ultimately, AI is not something that is great. I'm not talking about using AI. I'm talking about hardware which is going to perform. Ultimately, AI work on a hardware, so it requires a computing machine. Is it a conventional processor? No, it has to be specialized processor called accelerators. So what I'm trying to do is computer architecture itself is getting redefined. Now, future processors are, you have a main processor and you have an accelerator. So whenever it's an AI/ML application, you outsource the work into this accelerator chip.
Okay, sir.
Any other query from anyone?
We can understand, sir. You can proceed.
Okay, thank you. So once we understood the convolution operation, now let us try to understand what is neural network accelerator. So if you have a specialized hardware which consists of a grid of ALUs connected to a memory hierarchy, which will store your inputs, values, and weights and the outputs, and a neural network application. So you have a neural network which can be represented as a matrix format, like what is being shown, a product of matrix values on a specialized hardware. That is basically your ALU design. This together we call it as a neural network accelerator. This is exactly what is going to be the rest of the talk. Now, neural network accelerator can be of two types. One can be they are data flow architectures, or it can be architectures within memory technologies. Data flow architectures are of two types, temporal and spatial. And in-memory architectures, we do with hybrid memory cube and non-volatile resistive memories. Now, as the name suggests, data flow, the data is flowing, the inputs and weights are going to flow. Now, data flow architectures, let us look into, it can be temporal architectures like your GPU and CPU. You have a centralized control and a memory. Can you see this? This memory and then register. And you have a sequence of ALUs. So each ALU will load the value from the memory, perform the operation, put it back. Okay. But ALUs are not connected between them. ALUs cannot talk. That is the temporal and spatial architecture. That was something called single input, multiple data stream, or single input, multiple thread. When it comes to spatial architectures, you have a distributed control memory. Everything has its own registers inside. And the control. So you can see that here you have a memory. In the case of a temporal architecture, you have a memory. You have the registers and you have a control. Now the register and control is internal to the ALU. You have a global memory. From there, appropriate values are preloaded into registers. And each control will take care of when to add, when to multiply. And ALUs are internally connected. So the output of one ALU can go to the next one. This is known as spatial architecture or data flow architecture. So accelerators, most of the accelerators are data flow architectures. Now, you know that your data flow architecture means your data has to move. So what you see is you have a set of computation units. Okay. Now, from the set of computation units, these computation units are being given like W0, W1, like that. Computation units are there. You have a global buffer from which the input value, which is shown in blue color. So the inputs will come and the weights are kept already preloaded. So the weights will not move. I don't want my weights to move. The weights are preloaded. And so it's called weight stationary. You keep the weight in the processing element, input pixels and partial sums. They are going to move. So the inputs and the outputs will move. You can see that from one MAC unit, output is going to the next MAC unit, and that is already preloaded with W1. So I store, that's called weight stationary. I already stored the weights and inputs and outputs are going to move. Similarly, we can think of input stationary. The input value is already kept. The weights are moving and the outputs are also moving. Similarly, you can have the output stationary. So the inputs and the weights are going to move and accordingly you have to perform this operation. So these are the various levels by which data flow architectures are being defined. So someone was asking about what is the hardware inside this. So Iris accelerator is one of the popular one. If you look into, this is an accelerator chip. It has an off-chip RAM where you store initial values and then you can see you have a global buffer. So from the off-chip RAM, appropriate control signals will take the values into the global buffer. And then you have a data flow architecture there, where each of this MAC unit has some scratchpad and some control, some register and some control available. These are basically your processing elements. It's organized row-wise and column-wise. So input feature map, partial sum, everything is there. So lot of sequence. So the Iris accelerator works like this. So you have your global buffer, which will store your inputs and the weights. And accordingly, you have to move it. This is one such example of a hardware circuit which will facilitate. The another one is known as Simba architecture, which is also a very popular one. So it's a chiplet architecture of Simba. So what you see here is Simba package on the left side. This is a special accelerator circuit. It consists of multiple chiplets. Rather than having large number of units and its fabrication will become difficult. So you make it as rather than chip, you have a collection of chips that's called chiplets. Chiplets are now kept on an imposer, data imposer. And each of the chiplet, now if you look into, it has a lot of processing elements. And each of processing elements, if you loom into, you have weight buffers, you have MAC units, input buffers. So this is called a chiplet architecture, Simba package. And then each of them will be zooming into, and then this is what you get. And the other one is going to be the sequence of MAC units where the weight values and input values are being brought from memory and then put it over there. This was a significant revolutionary step. Then people note that This actually gave the bigger push for the AI wave to flourish. Because it's not only about AI programs coming, you require an equally supporting hardware. Unless the hardware is not there, none of these AI applications will be flourishing like this. So we want an architectural model that can support, which is different from conventional microprocessors. Now, in all these cases, we are moving your inputs and the weights values. So this data movement is very, very costly. If you look into the right-hand side, moving data from off-chip into the global buffer, from global buffer into processing elements, from processing elements, you are moving between them. So any movement, with, let us say with respect to an ALU to ALU or within ALU, let us consider it's a data movement cost is unit 1. Register file to ALU also is 1, but from one processing element to ALU, it may be 2 times data cost. Buffer to ALU 6 times, DRAM to ALU, it may be taking maybe 200 times. So if you really wanted to process neural network very fast, with a lot of data, it's very, very difficult because movement of this data is highly, highly challenging. So this bring data close to compute, physically closer. That's called near memory, and it's a hybrid memory cube. So there is the same place if you are going to. So one way that you can do is, can I bring data closer to the memory? That's what's called hybrid memory cube. The second one is, can I bring the data a little inside the memory? Then that is called resistive crossbar. So storage and processing, can I do it in the same place? Rather than you moving all these data, inputs and weights and then outputs, everything across the memory hierarchy into the accelerator chip. Can I perform the operation on where data resides? That is called in-memory computing. Can I do computation inside the memory? So that's why storage and processing are in the same place. Data movement is eliminated. This saves time and energy a lot. And we basically use analog computation. So you require dedicated circuits. So in the context of neural networks, the MAC operation is performed. We have to store the data and weights and perform MAC over there. Now, I'm trying to introduce a concept called memristor. It's a memristor crossbar. So what you can see that this is a memristor crossbar to perform matrix vector multiplication. So if you look at, you have voltages that is been given. This voltage is passing through this memristor and accordingly current is being produced. Now, if you look into that, your I1 is nothing but a vector product of the voltage values into what is there for, it is the resistance or the memristance, the impedance value. So if there is an artificial neuron like this, which has to be represented by a product of input and a weight, I can represent. So the equivalent circuit is your I, the current that is being produced is nothing but sum of I1 and I2, whereas I1 is V1 into G1. I2 is V2 into G2. So even though it's an artificial neuron, rather than writing a program and then getting, I represent the artificial neuron as an equivalent circuit where the weights are hard-coded as memristor values and inputs are represented as voltages. So when you give an input value, this input, analog value of this input will pass through the memristor and accordingly impedance is produced, and that is what is the current. So there is no data movement that is involved. What I'm trying to do, I'm trying to represent the weight of a matrix as a memristor value. So this is different layers of neural network. I can represent this like this. So you have a DAC. Your inputs values are digital, so digital to analog converter. And the sequence of memristor array will equally represent your weight matrix. Input values are converted to analog form, and when this analog signal propagate over this memristor, accordingly current is being produced, and then ultimately you shift back from analog to digital, shift and that. So I have completely eliminated data movement. Your input is being made to voltage. So this is actually 2 or 3 order of magnitude faster. So let us say the first one, the software approach using a data flow architecture took 300.
Sir, excuse me. In this, memristor value has to be changed. Is it possible to change the memristor value? Because normally we used to change weight, isn't it, sir? Weight has to be updated. Like that. Is it possible
Very
to
good
change
question.
the value of this memristor?
So the problem with the memristor design is I cannot change the weight. So I have to do the training, fix the weight. So this will be already trained system. Okay. So I have to find out the weights, and once the weights are finalized and converged, put up appropriate memristor values, and then hereafter it acts as a neural network. So the inputs only change now, and you get the corresponding output. So it's a weight stationary concept.
If it is, sir, if it is for one particular application, then we cannot change it for the another application,
No,
isn't it, sir?
no. So maybe it's a standalone device. For example, can you imagine maybe in your colleges you may using a biometric punching. So it has to recognize different people with the thumb that you show there. It's a standalone application. Had it been a memristor based device, it can quickly recognize rather than taking your value, sending it across, performing a neural network and finding out it's X or Y. This would be quick. So future it's going to be standalone devices, and these devices will be fitted with this kind of in-memory computing. Only problem is, suppose if you wanted to reprogram it, then these memristor values has to be taken out, and then you have to reprogram and then fix it.
Okay, sir.
Hope I clarified your doubt.
Okay, sir. Okay.
Okay. Any other query from anyone? Okay. So let me go to the next one. So it's basically a weight stationary data flow is what we are going to show. So based upon this, what we saw initially was it's a data movement architecture with some global buffer and then your MAC units. So can you reduce the data movement? That's exactly what you do by the ISAC architecture. So in this, if you look into, you have a set of tiles that you see. Each tile, if you zoom in, it has some buffer and some in-memory accelerator circuit IMA units. And if you look into each one of them, it has a crossbar. What is this crossbar? Memristor crossbar. The IMA is what is your memristor. So you have a DAC unit, digital to analog converter. It will go into the memristor unit and it will produce the corresponding output. So in short, the logical bird's eye view is a set of tiles. What is inside the tile? Inside the tile, we have some storage, some movement, and then the rest of the values are being. This is much, much faster than the other one. Similarly, we have something called NeuroSim. So this NeuroSim also has the same kind of a structure. So what I wanted to show is there are different kind of chips that are already there in the market. Here also you have global buffer, and then if you zoom in one by one, then you will be see. Ultimately, it is a synaptic array, which is nothing but your memristor array, which will be performing a weight stationary circuit mapping. This is one of the popular one. It's called SIAM. These are all free tools that is available. If somebody wanted to work with this, SIAM is an open source tool which will mimic. So you have a chiplet architecture. What I mean by chiplet means multiple chips are connected together and there is a network of package. So this is communicating between chips. So your neural network can be mapped on this. Now each of these chiplet, if you look into it, consists of multiple tiles. So you have a network on chip inside that. This is network on package, one hierarchy up. And each of the tile consists of processing elements. Each of the processing element consists of in-memory computing memristor crossbar. Okay. Now talk about multiple neural networks. So far we were talking about one neural network. Have you ever thought of a system which need to run two neural networks? You might have using this Alexa or speaker devices which can recognize speech and can do something. Okay. So what happens here is your voice has to be detected. So there are two neural network which work on it. One is keyword detection. So I wanted to listen to the song of Tyagaraja. I wanted to listen to the song of SP Balasubramanian. So what you have to do, I am telling something in words. From that, keywords has to be detected. That's one type of neural network. And then my speech has to be recognized. What I am telling. What is the word? I am telling about Tyagaraja. I am telling about SP Balasubramanian. I am talking about song. So first is detection of keywords. And once you know what is the word that I am talking. Similarly, we have something called hand detection and hand tracking. You are showing some symbols accordingly. The door has to be opened. Think of a case you are going to show your hand, and accordingly future main door of your house has to open. So there is a neural network which will work, which will detect hand. There is another neural network which will track the hand based on hand movements. So I'm going to talk about two applications working together. Similarly, eye segmentation and eye tracking. First of all, there should be one neural network which will work, which will find out where your eye is. That neural network would be totally different. The kind of weights, everything would be totally different in another neural network which will performing eye tracking. So in future, we have multiple neural networks that is going to work together, which is going to help. About multitask, multi-model, where we have a requirement of multiple neural networks to be running together. So this has to be run in real time. So both the neural network has to be really quickly fast. So what we'll do, we have only one hardware that is available, and in the hardware I can do only one neural network at a time. So can I divide the hardware, and one portion of the hardware will do neural network 1, other will do neural network 2. Are we going to stop with only 2? We may have even more than that. Okay. So what if 4 or 6 or so? Future is going to be, since AI is going to take up a big heap, the future is going to be, let's say 7 or 8 neural networks has to be working together in a system. So ultimately, all of them are convolutions, all of them are multiplication operations. So, and then the base is either your Mac units or your in-memory computing based memristors. What are you going to fix with that? So how do you do that? Classification of multitask, multi-model. I can do one after another. That is called cascade mode. First to do one model, let's say for first few microseconds, all the units are going to do neural network 1. After that, you move and then make it neural network 2. So it's one model. After that, the output of a model is going to be the input of the next one. Second category is called concurrent. Both the models are executing parallelly. Neural network 1, neural network 2 is going to execute parallelly. Then you have to divide the resources into 2. So it's called cascade mode and concurrent mode. So what you can do in the cascade mode, it is first to detect the face and then you recognize the face. But if it is concurrent, then semantic segmentation and obstacle detection both has to go together. Now, how do you do with this? We have two ways to handle it. One is temporal multitasking. So multiple tasks are there, multiple neural network is there. So temporal multitasking and spatial multitasking. So your inputs and weights has to be brought. Imagine, let us say you have a hardware with 16 accelerator chiplets. Chiplets or chip or whatever that you can talk about. Mainly 16 such big units. Now, each of this color, let us say this orange, blue, violet, green, they represent 4 different neural networks. So I have to run 4 neural networks. What I have is 16 of them. I can go what is been shown on the right hand side, spatial multitasking. So out of the 16 units available, 9 of them are given to the orange neural network, 3 is given to the violet, 3 is given to blue, and 1 is given to green. Some are big, some are small, some are medium type neural networks. So it's called dividing. It's a partition of your available resource. Whereas in this case, all 16 is given to all these 4, and you are using a time sharing mechanism. Everyone will spend some time and then you move it across and then you give it. So that is one way of doing. The other one is, do you really want it? So here in this case, all of them are uniform type resources and then you divide. These are all recent. Last year only this idea came. And this is called the idea of big little chiplet. Yeah.
Sir, one doubt. In the previous slide, green you gave 1 alone. So multiplication of that 1 alone will take less time. But
No.
instead 9.
This is not like that. Green is, let us say green consists of 32 Mac units. Okay, green is what is meant is, it is one neural network is completely mapped into one set of unit, which may internally have 32 Mac units.
Okay, but the same
Similarly,
thing, orange, 9 things are there, no sir. For all the 9 has to process, the time taken might be different. No, how will we do that?
That is what is the division all about. See, the orange neural network may have thousands of neurons, whereas the green may have only 100 neurons. So depending on the size of the neural network, we have to divide.
Okay, sir. The processing.
So you should know how complex it is. See, now this will all take same time. So, madam, what I'll ask is how much time you make to, how much time it is required to make a chutney versus how much time it is required to make a sambar. So one may be having more resources, one may be having very less resources. So accordingly, the kind of plates, the cooker, the utensils that you take will be varying. So it's just like I have a kitchen where I have 16. For example, you may just think of you are going to have about a big restaurant. There are 16 gas stoves available. Out of that, 9 gas stove is given for preparation of dosha. 3 of them is used for preparation of the uttapam, like that. So depending on, so there are lot many people asking for dosha. I have to reserve more resources for dosha. That's exactly the idea.
Okay,
so the
sir,
demand
okay,
is more, then hardware resource has to be partitioned. The other one on the left side, all thing can be used for everything. So for the first 2 minutes, the same tawa would be used for making dosha. The next time it may be used for making a paratha. Then again come back to dosha. That is called time sharing one, temporal. The other one is spatial. Hope I clarified it.
Yes, sir.
Okay. Now let us move
Sir,
into. Yeah.
Sir, excuse me, sir. Is it possible to give some more idea about this temporal multitasking and spatial multitasking, sir, please?
Okay. I will reuse the same that example. Okay. You
Okay,
are
sir.
going to talk about a restaurant where multiple food people can come and ask for different types of food. Let us take dosha is there, paratha is there, the uttapam is there, some idli is there. So, and then what you see here is your kitchen, which has total how many burners, the cooking knob, what you see in the gas, okay, tawa. You have total of 16 tawas. Now, at one point of time, a group of friends came, they all wanted dosha. So then I can use of the tawa for everything. And then somebody else came, they want uttapam, somebody else came, they want parota. So what you do on the left side, temporal multitasking is I can use all the tawa for making everything, but there is no specific division given. Okay. So the same tawa is used for everybody. The other one,
Yes, sir.
I am dividing, physically dividing. Let us say I anticipate that the number of people demanding for dosha is very high. So I am making use that this 9 of them is dedicated only for dosha preparation. The 3 is used only for the violet one. This is spatial. So my available resources in hardware will accept only certain neural network categories. So I'm talking about a system with 4 neural network is running. Are they running everywhere or are they running in specialized place?
Thank you, sir. Got it, sir.
Okay. So any more doubt in this? So the idea is when multiple neural network come, how should my hardware adapt to it? Hardware is open for all so that one after another you will do. There is no specific allocation that has been there. Okay. So the same way that you can think, there are 16 chairs that is available for first year, second year, third year, and final year students in your college. 9 chair is reserved only for final years. So the final years will come and only sit there. Or
Sir, actually,
any chair can be used by
sir,
anyone.
sorry, sir. Actually, there is a time sequence data which has some temporal relationship from the earlier data, maybe in computer vision applications or maybe in languages, NLP kind of things. That's why I tried to ask that one, sir, in this temporal.
Sure, I will tell one again. This is not one MAC unit. Okay. Inside each box, there can be 32 or 64 smaller MAC units. So
Okay,
this
sir.
is not
Okay,
the
sir.
actual unit. Once you open, you get, so the moment this green one, what I'm telling, this green, if you open, that has 32 different MAC units that is there. 32 units. So each one would be, the neuron would be mapped into that.
Got it, sir. Got it, sir. Thank you.
So the timing between them, you have to schedule. So only after one neuron, its output has to be gone. So previous data has to go to the new one. Then accordingly, you have to schedule. So the problem basically happened because there is only one for green. No, that's only one major chunk. Inside that, everything is for green. It's one level of the abstraction above. Moving forward, now we have big little chiplets. Why do you want to make all units of exactly same type? Okay. So you have big pressure cookers at home, small pressure cookers at home. So today you decide, okay, this curry I'll make in small, this curry I'll make it big. Now the question is, inside your kitchen, how many big cookers, how many small cookers? So I have, let us say, 8 small cookers and 6 big cookers. This is called little chiplet. Other one is known as big chiplet. So certain neural network requires, so the big chiplet may contains 200 MAC units inside, whereas little may contain only 50 inside. So depending upon, so all this comes when it comes to multitask multi-model. When you have a neural network, multiple neural networks coming, where do I do? So I have to come up with chips which are of varying capacity, chiplets of varying capacity, such that if there is a small neural network, I can schedule them on a little chiplet. If I have a big one, or I can schedule maybe on 2 little chiplets, I can use combinations, whatever that has been shown. So this is called the big little chiplet concept. Only thing is I'm giving a superficial view. So the idea is multiple neural network when it has been coming, what should be the underlying hardware which should do? If hardware all are same, will not scale. So the other one also you can see that we have 4 big guys and 9 small guys is one chiplet or one group. So group number 0, what you see, can take multiple neural networks. It's up to them. Should I use that? So it's like 4 luxury. This is like a movie theater. Okay. You have 4 big luxury super class chairs versus 9 common chairs where you wanted to go and sit. Depending upon how rich you are, you can plan. So it's a scheduling problem. Provide an optimized in-memory computing architecture for multitask and multi-modal workloads. So we optimize the design based on the number of networks, the size of networks, the intercommunication between the networks. What are the challenges to be addressed? How do you group? That's one question. What should be the size of network versus the chiplet count? What is the optimal input data flow? And how do you move data from one to another? So I am coming to the end of the talk. What is the takeaway? Over the years, the programs that are running on computers have broadly changed. Nowadays, everything is machine learning application. And it's going to exponentially improve. Machine learning application. What is this ML application? They are merely programs. But these programs are running in such a way that it's mimicking like a human. It can change text. It can write words for you. It can create new faces. All that was previously impossible. Now it looks like many of these very complex tasks which only human beings can do. Now your AI system is doing. Can AI be treated as simply like a program? Yes, it's a program. But our conventional hardware may not be good enough. So you require specialized hardware. Okay. Why you require a special kind of a cookery vessel for idli making, and why you have a flat surface for dosha making? So application, it's all food. Okay. Rather than all of the utensils look similar, we are going for customized one for idli or for different kind of items. It's a different kind of vessel that you need. The cookery vessels that you need. This is called accelerator. So the idli vessel cannot be used for making something else. No, you cannot make a dosha on an idli vessel. So handle data well, that's one concept that we learned. So with emerging application, you need to redefine your conventional microprocessors. So ensure data does not overwhelm the components. How do you do it? With so much data, inputs and weights has to be quickly processed for different layers. If you are from computer science background or IT background, you can look for intelligence algorithms you can do. If you are from electronics, if you like VLSI signal processing, you can do with intelligent architectures, or it can be a combination of both. Since there are a lot of data that has been involved, it's good that if you process data on where it resides, processing can be in and near memory structures, like what we learned. Now, since a lot of data, I should come up with, so memory technology is equally good. I don't want to think of, you are thinking that, okay, I don't know my AI much. All my friends are talking about AI, but my research domain is not AI. How do I go in this modern world? Please understand, AI means it's about storing of inputs and weights, and they are continuously read and written. So it's a memory. It's a flip-flop. So if you are good in memory design, SRAM and DRAM and whatever we are talking, we require low latency and low energy data access. Then only your AI will go good. Or else if memory is very costly, power consuming, AI cannot work well. So low latency memory designers. If your students do something on memory design, which are low latency, low energy memory, it's good. Since you store a lot of data, I require a lot of storage space. Can I do something on it? We require compression. Can I compress the inputs and weights and store? Then hybrid memory, SRAM and DRAM and NVRAM, different types of memory, high capacity memory at low cost. And then where do I store? Can I store all the data the way how I want, or some intelligent data management by intelligent controllers handling robustness, security, cost, and scaling? These are the ways in which people are now broadly looking at it from this perspective. So I'll take a little more time on Q&A. I'll tell about opportunity. So what I wanted to convey ultimately is machine learning applications will dominate future computing systems. ML cannot work on concrete. ML cannot work on paint or timber or wood. ML can work only on a computing system. So the computing system also has to go along with the ML world. So effective leverage of AI and ML can be possible only with ML-friendly hardware. Ultimately, the hardware is saying no revolution is possible in AI ML field. It's possible, but it takes time. So AI engines and ML processors will rule the future world. What India needs to scale up manpower with a passion and skill to contribute to building compute system that augment the AI growth. Okay, that's all what I wanted to convey. I'll be happy in taking questions. Please do understand, when we as teachers, I understand it's an adult FTP, we should be well versed with what is happening in this domain, or else in the next 4 or 5 years, teachers will become obsolete. Students will feel that it's very easy to get this contents from internet. Now the question is, you should think of why should students listen to our classes? Why should they come to college? If we should be teaching something which is not available in internet. If everything is available in the internet, they will feel internet classes are good. Now think of a case that you sometimes when you watch in YouTube also, you may feel certain way, suppose one NPTEL class A is better than another NPTEL class B. Maybe a faculty's explanation, expression, and the way how they teach may be good. Now in future, it's indeed possible. And nowadays also, especially old dead political leaders, they, with the help of AI, their speech is been recreated. So if somebody is a very good teacher, if I give a text, and if I know the video model of a teacher, I can generate any number of video class with this text. So I am giving you text and you are simply going to read. So news reading, you just imagine the future news reading is just going to be a person's robot kind of a person who is going to sit and the text has to be converted and then they will read news. So certain field is going to become obsolete and certain fields are going to be totally newly emerging. So classrooms can become obsolete. What if it's all needed is a screen? Let's say TV is kept in a classroom and then you configure it. So let's say some great teachers teaching in Delhi, it can be webcasted to every room in every classroom in the class there in the city. Okay. So now we don't know. Maybe 10 years down the line, even AICT can come and tell there should be only very few teachers. The balance all can be 3D models of teachers. For example, let's say John is a very good teacher. Just imagine. And if his class is good, this can be recreated in every nook and corner of the country. So the government's enrollment ratio, if they wanted to improve the number of students going for higher education, and if some teachers are not effective, it can get easily replaced with the future AI models. So as teachers, we have to reinvent, or else 10 years down the line, we have no idea whether there exists a profession called teaching or everything will be overtaken. Don't know if the profession of a simple consultant, a physician, will be gone or not. If you can train a system which know all the diseases. Okay, nowadays doctors are what? Either cardio or nephro or gynecology or pediatrics, whatever. They will specialize only in ones. So future AI robots, you can make the robot mode 1 means the robot act as a cardiologist, mode 2 means robot act as a nephrologist. So the simple consultation, 24 hours the robot can work. A simple consultation, so you can have a lot of consultation rooms. Maybe the hospitals may think, why should I pay this? So doctors may do only surgery or very high-end things. The routine consultation. See, what do you do when you go and see a doctor? You will check your temperature, pressure, heartbeat, and from experience of doctor, he is diagnosing. Okay. So I don't know. Down the line, the world will change. We have to also adapt. But ultimately, one area that is safe and secure is computing systems. Nothing without computers or new model of computers. So embracing students, telling the students that investing on computing system is more important than barely become coders. There are 2 ways in which, or there are 3 or 4 ways in which AI is going to impact us. Some people are mere users of AI. There are a lot of AI apps. I will be the user. Second one is people who will little bit contribute to the AI. They will make use of these AI applications to make their job easier. The third one is going to be those who develop new algorithms for AI. And the fourth class is those who develop systems. It can be hardware, it can be operating systems, it can be IoT devices. Those who make systems which make AI a big reality to the nook and corner of the country. So this is what I wanted to tell. Thank you. If there are any questions, I would be very happy to take.
Thank you, Professor, for a very interesting talk. So any queries from the participant side? Any queries or clarification from the participant side?
पूरा ही बंद कर दिए हैं इसमें वो इसमें अटल वाले पे जा इसमें एक लिंक आया हुआ आज में आया हुआ ना नीचे और ऊपर कर इसको स्क्रॉल कर टुडे हाँ तो टुडे से नीचे जाएगा ना अब ये
हेलो
और कर
मैम यू हैव एनी क्वेरी
I think no more questions from participant side.
No, sir.
No queries, sir. No queries, sir. We are sincerely attending classes. SAR session. SAR session was very good. 1 or 2 participants maybe unmute their mic and talking irrelevant. Sorry for that, sir. Behalf of my side, please forgive them. And your session is entirely good. And how much ever AI gets a boom, artificial intelligence cannot take over the physical human intelligence. That's my opinion. Definitely we take your suggestions and we'll improve, and we tell students to take some computing systems and get what good knowledge in the computing. Thank you, sir.
Thank you. Welcome to all and wishing you all the best, the very best.
Thank you very much, sir.
Thank you, Professor. The session was very informative, Professor. Thank you very much, Professor.
Okay. Good night to all.
Yes, Professor. Good night,
Thank you, sir.
Professor.
Thank you, sir.
Thank you. Thank you. Thank you.
Thank you, sir.